So, do you remember the law of conservation of energy? If you do, remember what that means is different types of electromagnetic energy cannot be created or destroyed. In other words, that energy doesn't disappear, it's only transformed. And that's what we're going over with this image intensifier tube. At the input phosphor, as a reminder, we get X-rays, a type of electromagnetic energy. They're converted to light and then to electrons. Those electrons are accelerated to a focal point where it's then a mini image of what we got here, the information we got here, and then it's further accelerated to the output phosphor, where it will be eventually taken to the screen, and we can actually see everything. So, flux gain is the number of output light photons over the number of input X-ray photons. It's basically an expression of what we got here compared to what we're getting here. Minification gain is the diameter of the input phosphor over the diameter of the output phosphor squared. So it's kind of an exponential difference. One thing to notice is the size of the input phosphor compared to the size of the output phosphor. They try to give you a hint here with the color that they use as well. You can see here it's a lighter color, and then the color that they try to use here intensifies as it goes along until it's pretty dark, much darker than it started. That's kind of like the same for the electrons or the intensity. It was broader here, and now it's more condensed here. Finally, conversion factor is an expression of the output phosphorillumination, so basically our brightness up here, over what we got here at the beginning. So multifield image intensifiers is likely what you're going to deal with. They're usually in 25, 17, and 12 centimeters. Now what that means is you can have a 25 centimeter image, you can magnify it to a 17 centimeter image, or you can further magnify it to a 12 centimeter image. Now I know I'm saying magnify, which makes something look larger, and in the meantime our measurements are going down. But all it means is think of getting an image on your computer, let's say here. And let's pretend that the smaller I make it, the less area you can see, so it appears larger. So while my field of view might look smaller, the image itself looks larger. So at 17 centimeters and 12 centimeters, the voltage on the electrostatic focusing lenses is increased, and that causes the focal point to change. So if we take a closer look here, we can see the 25 centimeter focal point is closest to the anode. The smaller the focal point, the further away it gets from the anode. This decreases the total size of the input phosphor electron diameter that we're going to use, which they try to show you here. The change in focal point reduces the field of view and results in a magnified image. So magnified fluoro requires an increase in technique and patient dose, since less photoelectrons are used. So if we didn't increase the technique, the image would appear too dim. But usually MA is increased by the automatic brightness control. A thing to remember about magnification mode if you are using it in fluoro is that, again, it does increase dose, but it improves signal to noise ratio and that it lowers noise. It can improve image contrast, but it reduces brightness at the edges, which is called vignetting. But it can also improve spatial resolution, or it gives a high line pair per millimeter measurement. Finally, what happens after the output phosphor, you might ask? Well, from the output phosphor, we have fiber optics or lens coupling that attaches it to this camera tube. We can see another conversion of energy to where we get electrons, an electron beam, that interacts with other components to give us that visible light that we ultimately want to see.